Are radicals really irrational? In order to discuss radicals, we have to talk about the irrational numbers. If n represents the natural counting numbers, 1, 2, 3, 4, etc., then z, the set of integers, are the positive and negative whole numbers. Q for quotient is the set of all ratios of integers, called the rational numbers, where that ratio of two integers have no common factors. The irrational numbers are numbers that are not rational. Some famous examples include pi, the square root of 2, e, and the golden ratio of phi. All irrational numbers, given as decimals, exhibit the same property. That is, their digits never terminate, and there's no discernible pattern to the digits. Yet we can split the irrational numbers into two separate camps: algebraic numbers and transcendental numbers. The square root of 2 is an algebraic number where pi is transcendental. Algebraic numbers are those irrational numbers that are the result of solving an algebraic equation. Algebraic irrational numbers are given by roots or radicals. The discovery of irrational numbers came largely from the Greeks, the ancient Greeks, the Pythagoreans, studying right triangle geometry. The diagonal of a unit square has a length of the square root of 2. Now, when it comes to numbers like pi, circles give rise to this transcendental number. Transcendental numbers are not the solution to an algebraic equation. They transcend algebra. But yet, anything involving circles, we can find pi involved. The circumference formula is pi times the diameter. Yet pi, for many centuries, was attempted to be approximated using a rational number. Now, all radicals are algebraic irrational numbers. They'll be the focus of what we talk about today. The square root of 2, which is approximately this irrational number given as a decimal, can be proven to be irrational. That is, not the ratio of two integers. And since 2 is a non-perfect square, its square root is not an integer or whole number. Now, do radicals exist that are equal to a whole number, but where the radicand, and we're talking about square root radicals for now, are not necessarily perfect squares? Are all non-perfect square radicals irrational? A continued radical is a nested radical, and it'll be the focus of our video today. They take the form that look like this, where a, b, c, and d are typically integers but could be real numbers, and we question, does this equal a limit, L? To simplify this, let's let a, b, c, d, all those real numbers be the same number, n. So we have this continued radical with just the same number n involved. and we'll let that be equal to the limit L. Now if we add n to both sides of this equation, we get this. And if we take the square root of both sides of this equation, the right-hand side is equal to L. Therefore, we may write the equation L plus n equals L squared, or L squared minus L is equal to n. Now, L is equal to this continued radical, and now with this formula we can find the n that goes with a specific L. So let's say we want the limit of this expression to be equal to 2. That would indicate that from our formula above, n must also be equal to 2, giving us this unique expression: 2 is equal to the nested or continued radical, all containing 2's. This radical is equal to a whole number, suggesting that the radicand inside there is the perfect square 4. That's pretty strange. What if we want the limit to be 7? Well, then the n, by this formula above, would have to be 42, and therefore the continued radical for 7 would be given by this. Now, if you question if this is really equal to 7, let's do a few approximations. Starting with the square root of 42, and then the square root of 42 plus the square root of 42, continued radicals, successively approximated here, show us that the limit is in fact approaching 7. Now, consider the natural numbers 1, 2, 3, 4, etc. And as a quick side detour, let's consider the continued radical with this sequence of numbers. So the continued radical 1 plus radical 2 plus radical 3 plus radical 4, etc. What kind of limit would this approach? Does this in fact approach a limit? Another way to ask that is, does it converge? Another sequence to consider might be an alternating sequence, such as 1, 2, 1, 2, etc. Creating the continued radical with that sequence, one might ask, does this have a limit? Does this converge? See if you can figure it out for yourself, but we'll talk more on this later. A curious result from our formula from before. Recall that L being equal to the continued radical where all the n's, all the numbers inside the nested radical are the same, and L squared minus L is equal to n. Let's say we want to choose a very unique limit, like the golden ratio phi, an algebraic irrational number. So let's make the limit equal to this number, and the golden ratio, phi, obeys this quadratic equation, which gives us phi squared equals phi plus 1. Now, utilizing that in the limit formula to find n, we discover that for phi, n must be equal to 1. Now, why is that a curious result? Well, as a continued radical, phi is the simplest continued radical with all ones. And in my last video, I showed it's also the simplest continued fraction, including all ones. A beautiful result. Now for something a little stranger. Testing the limits of the formula here, what if we wanted L to be equal to, let's just say, 1? right? So let's let L equal 1. What does that indicate N must be? Strangely enough, N works out to be 0. Put it another way, 1 is equal to the nested series of radicals with all zeros? What's going on here? Your objections are noted. If we do a construction from the ground up, in other words, build this radical of nested zeros, what kind of approximations are we going to see? Well, we see here that we continuously get zeros if we build it from the ground up. So the limit looks like it's approaching 0. In fact, it looks like it's exactly equal to 0. So which one is it? Is this series of nested zeros in the radicals equal to 0 or equal to 1? Could it be equal to both? Examining the formula for n, we can see that it is a quadratic formula involving L. So the quadratic formula can tell us that L is equal to 1 plus or minus the square root of 4n plus 1 all over 2. Now, examining the discriminant there, if we want L to be a real number, then we can't have a negative under that radical. So 4n plus 1 must be greater than or equal to 0, which means that n must be greater than or equal to negative 1/4. If we restrict n to the integers, that means that n must be greater than or equal to 0. So you can play around with that formula to see what happens if you start to break that formula. But it indicates here why there are two solutions to L. For square roots, we then ask the question, are both solutions valid? Or is one solution extraneous? And it really boils down to how you ask the question. If we take the limit as n approaches 0 of the existing infinite series of continued nested radicals, we get the value of 1. However, if we construct the series of nested radicals with all zeros in them from the ground up, we get 0. And I leave it to the viewer to understand the difference of why that is. Can you figure it out? Ramanujan strikes again. In our last video, we discussed some of the important results of the Indian mathematician Ramanujan, and here we'll do that again. Consider a sequence of numbers a1, a2, a3, etc. Ramanujan showed the following result. The following formula holds true for continued radicals. So, let's use this formula to see what kind of results it can produce. If we let x equal 1, a1 equal to a half, a2 equal to a fourth, a3 equal to 1/8, and so on, where we're taking successive powers of 1/2 for the sequence, we get the continued radical here to equal 1/2, where we have an alternating radical 1, 1/2, etc. It's a very interesting result. But if we choose, say, some different values of x in the sequence here, like x equals 3, and the sequence a1, a2 is just a alternating sequences of positive and negative ones, we get this particular result. How Ramanujan saw this really speaks to his genius, but a condition here is that the first sequence term must be less than x. To look at a more general formula, let's consider a number that is built from x plus n plus a. The following continued radical formula holds true and can produce some pretty interesting results. Let's let x equal 1, n equal 2, and a equal 3. And that tells us that 6 is equal to the square root of 28 plus square root of 34 plus 3 times the square root of 40 plus 5 times the square root of 46 plus etc. A very unique result. What can you create with that formula? Another important result, which helps us examine this idea of continued radicals and whether they converge to a number or not. Consider the continued radical with the following sequence a1, a2, a3, etc., where a sub n is greater than or equal to 0. This will converge to a limit if and only if the limit of the natural log of the sequence divided by 2 to the nth power exists. So this gives us a way of testing for convergence. Now, recall the square root of 1 plus square root of 2 plus square root of 3 plus square root of 4, etc. example that we saw earlier. The sequence was the natural numbers given by n. If we ask the question whether the limit exists of the natural log of our sequence over 2n exists, then what we would get is the continued radical would have a limit that can be found. In other words, it would approach a limit, it would converge. So the limit of the natural log of an over 2 to the n would be the limit as n goes to infinity of natural log of n over 2 to the n. So if we examine what some of these sequence terms are going to look like, the natural log function grows slowly where the exponential function grows very fast. So it looks like this would approach 0. But just to be sure, let's apply L'Hopital's rule to this limit and take the derivative of both the top and the bottom to see what result we get. That gives us the limit as n approaches 0 of 1 over n 2 to the n natural log of 2. And that will approach 0, which means the limit does exist. This particular continued radical has a limit. Can you figure it out? Math is pretty radical. And thanks for watching. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.